Okay. Now this is a dominant and insignificant pole definition. Now in the same question, now the control system to be stable, what should be the conditions? That also we will see. A control system to be stable, what should be the points we have to be identified? Now, which we already finished the first point. What I am saying is the response should be follows the input. The response of the control system, the response follows the input, then that control system to be stable, which means for bounded input, the response follows the input, means for bounded input it should be bounded output. For finite input it should be a finite output, then that control system is said to be stable. This is the first point. And second point, this is one easy method to identify the closed loop control system or control system to be stable. At t tends to infinity, the response is finite. At t tends to infinity, the response is finite, then the control system is to be stable. You just check that previous question. Now this is the previous question. This is the response. Now in the previous question, now this is the response. What is the response? The response C of t, which is equal to -1 into e power minus 2t plus 2 into e power minus 3t. What this point 2 is saying is, at t tends to infinity, in the response, if you substitute limit t tends to infinity in the response, then what happens? You see here, -1 into e power minus infinity plus 2 into e power minus infinity at t tends to infinity, which means what? Now this is 0 plus 0, which is equal to 0. Now at t tends to infinity, the response is 0. The response is 0 means the response is finite or not? The response is 0, which is nothing but finite. This is 0 plus 0, which is equal to 0. This is finite. Then the control system is to be stable. Now that's why this is a easy method. At t tends to infinity, substitute in the response, where in the response at t tends to infinity, the response should be a finite value, then the control system should be stable. Now, and this is the second point. And the third point, which is very easy point to you, which we already finished. Now see here the closed loop poles. Where are the closed loop poles? Now this closed loop poles, this is the closed loop pole. Now this closed loop poles lies on left hand side of S plane. If the closed loop poles lies on left hand side of S plane, then the closed loop control system is to be stable. These are the 3 points you can easily decide it the closed loop control system is to be stable. What are the 3 points? If the response follows the input, now means for bounded input, then the output should be bounded, then that it should be for bounded input, the output should be bounded, then it should be stable. And at t tends to infinity, here is the example. At t tends to infinity, the response is finite, system is stable. And if the closed loop pole lies on left hand side of S plane, then the closed loop control system is to be stable. That's what now in the S plane, now see here, this is the S plane. Therefore, in the S plane, this is left hand side of S plane. This is left hand side of S plane. If the pole lies only left hand side of S plane, then this is the stable region. If the closed loop poles lies only on left hand side of S plane, now left hand side of S plane, then this closed loop control system is to be stable. These are the 3 important points you can easily identify that when the control system is to be stable. No doubt. Okay, now this is the 3 important points for the closed loop control system to be stable. Now let us take one example here I am taking. Now this is the closed loop control system transfer function, which is equal to, now this is the transfer function which is given to you. Now this is the closed loop control system transfer function. Now this is C of S by R of S, which is equal to 1 by S minus 4. Now this is question number, this is question number 5. This is question number 5 in your workbook. Now this is question number 5. What is question number 5? Now, by considering the closed loop control system, C of S by R of S, which is equal to 1 by S minus 4. Now, what is the question is he is asking? Find all the parameters. Now, in a one statement he is giving, find all the parameters. All the parameters means all, whatever you are able to calculate, all the parameters you are calculating. Okay. Now, this is question number 5 in our handbook. Now, find all the parameters. Then we will, whatever we solved previously, like that we can solve. Now, first, where is this pole location you identify? Is there any poles or zeros? Yes, there is a pole. Where is this pole location? S minus 4 equals 0. S equal to plus 4. S equal to plus 4. This is a closed loop pole. How many closed loop pole? Only one closed loop pole. Therefore, order equal to. Therefore, only one closed loop pole. Therefore, order equal to 1. Right. Therefore, next. Is there any imaginary part? No. Only real part. How you can say? Now see here, only one closed loop pole, therefore order equal to 1. Therefore only one closed loop pole, order equal to 1. Now this is your question number 5 in your workbook. Now find all the parameters, therefore one closed loop pole, therefore order equal to 1. Now the question here is, what I am asking is, now one closed loop pole, order equal to 1, then is there any imaginary part? No, the pole is having only real part, no imaginary part, only real part. Therefore, if there is no imaginary part, now see here, no imaginary part, only real part. Therefore, the frequency of oscillation is no imaginary part, only real part. Therefore, frequency of oscillation present in the response is 0 radians per second. Next. Now you see here. Now, if you want to see the response, first we want to apply the input. Then you want to apply the input. Then I am already saying, for theoretical analysis, for mathematical analysis, the best input is an impulse input. Now this is the impulse input. Now Laplace transformation of this impulse is 1. Therefore, now see here, C of S, which is equal to R of S into 1 by S minus 4. What is R of S? R of S equal to 1 into 1 by S minus 4. Now this is the closed loop control system response. This is the closed loop control system response. Now this is nothing but impulse response. Now see here, this is the closed loop control system response, which is nothing but the impulse response, because I am applying which input? Impulse input. Therefore, now see here, C of S, which is equal to 1 into 1 by S minus 4. Then I want the response in time domain. Apply inverse Laplace transformation. Therefore, C of t, which is equal to e power plus 4t. E power plus 4t. This is nothing but the closed loop control system response or impulse response in which domain? This is in time domain. Then, if you have any doubt, again you will see here, this is the closed loop control system response. This is the impulse response. This is in frequency domain. This is in time domain. Now, if you observe, the response always consisting closed loop pole. What is a closed loop pole? Plus 4 is a closed loop pole. Now, this plus 4 is nothing but a closed loop pole. The impulse response, any control system response consisting only closed loop pole, plus 4 is a closed loop pole. Now, what is the response? Draw the response in time domain. Now, see here. Now, what is the response? Now, this is the closed loop control system response. This is the impulse response in time domain. Then this response, if you draw, now what is the response? Now the response is exponentially increasing. If t equal to 0, e power 0, which is equal to 1, now this response is exponentially increasing. This response which is exponentially increasing. This response which is exponentially increasing. And one more thing also you are saying, what is the frequency of oscillation? Now from the pole's location, the frequency of oscillation is 0 radians per second. But is there any oscillations here? No oscillations. Therefore the frequency of oscillation is also 0 radians per second from the response. This is from the response. Now from the response, you are saying the frequency of oscillation is 0 radians per second, and from the pole's location, no imaginary part, only real part. Therefore, the frequency of oscillation is 0 radians per second. See here, in the pole's location, no imaginary part, only real part. Therefore, frequency of oscillation is 0 radians per second. And in the response, there is no oscillations. Therefore, the frequency of oscillation is 0 radians per second. Both are matching, is correct. And the response is exponentially increasing. And this is exponentially increasing. Now with respect to time, on the time axis, now I am giving the inputs. Now see here. In the response, now I am giving the inputs on the time axis. The response does not follow the input. The response is moving away from the input. Now see here, the response is not follows the input. I am giving the input, but the response is not follows the input, and it is moving away from the input, and it is moving towards infinity side. The response does not follow the input. The response is away from the input and moving towards the infinity side. The response does not follow the input. Then that system is said to be unstable system, and that response is unstable response. This is unstable response. Unstable system. The response does not follow the input, then that system is an unstable system, and that response is an unstable response. If the response does not follow the input, now unstable. Am I not? This is an unstable system. Then one more parameter, you find the order, now you find the response, you find the behavior, and you find the system stability, you find the frequency of oscillation. Then what is the time constant? So can I write like this? The time constant, which is nothing but negative of reciprocal of real part of the pole, which is plus 4, which is equal to minus 0.25 seconds. This is a wrong answer. This is wrong. Why? So the time is minus 0.25. A time will never be minus, okay? And this is 100% wrong. Now here you cannot find the time constant. We cannot find the time constant here because Now the system is an unstable system. The time constant is calculated only for the stable responses, because the time constant is one of the system parameter which will change the behavior of the system. Already the system behavior is an unstable response, unstable system, where we cannot find the system time constant. The system time constant is calculated only for stable responses. Only for stable systems we can find the time constant. For unstable systems we never find the system time constant. Okay. Therefore, we cannot find the system time constant. This is wrong. Anyway, you take this one also. This is wrong. We cannot find time constant. We cannot find time constant. Take this one. Take this part. Okay. This is question number 5 in our workbook. Now we find order and we find frequency of oscillation, and it is matched in the response or not also we will see, and we will draw the response, and this is the response. Based on the response you decided the system stability, and we cannot find time constant because the system is an unstable system. We cannot find the time constant. Now take this particular portion. Okay, then here this note also we will take. We cannot find the time constant. This is wrong. We cannot find the time constant because system is unstable. This note also you have to be considered. Take a note here. What is the note? Take this note. System time constant is calculated only for stable systems. Time constant is calculated only for stable systems. Time constant is calculated only for stable responses. For unstable response, we cannot find time constant. Unstable response itself, the response does not follow the input. The behavior is not follows the input, then we cannot find that particular system. Because the system time constant is one of the system parameter, we need to change the behavior. Therefore, the system time constant is calculated only for stable systems. Therefore, don't find the time constant first. First you find the system stability. If it is a stable system, then you go for calculation of system time constant. If it is an unstable system, there is no need of calculating the system time constant value. Okay, then you take this note. Okay. Then similarly, what we are doing here is Just now we finished. Now we'll take for this. Control system is to be unstable. If the control system is to be unstable, then what are the points? A control system is to be stable. Just now we write a few points. The same points we will writing for a control system to be unstable also. Now see here, when the control system is to be unstable, just now we finished the response. The response follows the input, means system is stable, but the response does not follow the input. The response does not follow the input, then the system is unstable, which means for bounded input, we are giving a bounded input, we are giving a good input, but it produces, we are giving a bounded input, but it produces unbounded output. Now, the response does not follow the input, then the system is unstable, which means for bounded input, it produces an unbounded output. Now, for bounded input, it should be an unbounded output, then it should be unstable. And similarly, at t tends to infinity, the response is finite, the system is stable. At t tends to infinity, the response is infinite. This also we will check here. At t tends to infinity, now this second point you will check in the same problem. This is in the problem. What is the response? This is the response. The response C of t, which is equal to e power plus 4t. Now what happened? Now see here, the response at t tends to infinity, the response at t tends to infinity is C of t at t tends to infinity. Now the response at t tends to infinity, which means that e power plus 4t, which means that e power plus 4 into t is infinity, which is equal to infinite. At t tends to infinity, the response is infinite. This is infinite. Now at t tends to infinity, the response is infinite. At t tends to infinity, the response is infinite. At t tends to infinity, the response is infinite, then the system is unstable. Yes, this is the previous problem, which is an unstable, and therefore at t tends to infinity, the response is infinite. Then we will cross check. Yes, this is matching. And no sir, all these things are, I don't want sir, I want a shortcut method, easy method. By looking the problem, I want to easily say yes. Therefore, this is an unstable system. The previous problem, this is unstable system. Where is the pole location? You just observe. This is an unstable system. The pole location is, this is the unstable system. This is the unstable system. The previous problem is this. This is the unstable system. If it is an unstable system, where is the pole? Pole is on the left hand side or right hand side? The pole is on the right hand side. Therefore, if the closed loop pole lies, on right hand side of S plane, then the closed loop control system is to be unstable. Which means that if the closed loop poles lies on right hand side of S plane, if the closed loop poles lies on right hand side of S plane, if the closed loop poles lies on right hand side of S plane, if the closed loop poles lies on right hand side of S plane, now this is nothing but an unstable region. Therefore, these are the 3 points which previously we are saying a closed loop control system to be stable. In the same manner, if the closed loop control system or a control system to be unstable, and these 3 are the important points. And here is also we can cross check at t tends to infinity the response is infinite. Yes, in the previous problem at t tends to infinity the response is infinite, therefore system is unstable. And in the same problem, if you observe here, your pole is on right hand side of S plane, therefore system is unstable. Therefore, these are the 3 important points for the system is unstable, and previously we will see the 3 important points for the system to be stable. Then you just take this one. Now with the same manner we will have one question. This is question number 6. This is question number 6 in our workbook. Question number 6. This is a 2 marks question. This is a previous GATE 2 marks question. Is a question number 6. The open loop transfer function. What is the question number 6? This is 2 marks question, which is very simple. Only based on basics he is giving. Only based on the basics of the time constant definition. This question you just observe. But he is giving for 2 marks for the previous GATE examination. Now, the open loop transfer function of a DC motor, which is given as omega of S by VA of S. This is the open loop control system of a DC motor, which is given as 10 by 1 plus 10 into S. 10 by 1 plus 10 into S. When it is converted into feedback as shown below, the approximated value of Ka such that the time constant. So anyway, the question is related with the time constant. So this is a open loop control system. This is the open loop control system transfer function. This is open loop control system transfer function, which is given to you as this much. So from here, first you want to find the time constant. What is the time constant? Time constant, if you want to find, first we want to see the pole. This is the open loop control system. Where is open loop pole? 1 plus 10 as S equal to minus 1 by 10. S equal to minus 1 by 10. This is the open loop pole. This is the open loop pole. Now you find the open loop control system time constant. What is the time constant of open loop control system? The time constant of open loop control system, which is equal to minus 1 by 10, which is equal to 10 seconds. This is the time constant of open loop control system. Then what he is saying is, this is the open loop control system transfer function of a DC motor. When converted into feedback, this transfer function is converted into feedback as shown in the figure below. When it is converted into feedback as shown in the figure below, the figure is also given. Again, I am drawing that, not a problem, but that is there in our handbook. When it is converted into feedback, this open loop transfer function of a DC motor is connected with a feedback. Then how it will be appeared is, now it is connected like this. It is connected into feedback like this, 10 by 1 plus 10 into S. See here, Now this is the open loop transfer function, and whose control system, open loop transfer function, open loop control system whose transfer function is given, and this is the time constant, and this transfer function is converted into feedback. Now he is giving a unity feedback, and it will be changes are this, and it is converted into feedback like this. Therefore, now he is asking the time constant of closed loop control system. Therefore, now for finding the time constant of open loop control system, we need open loop pole. Once if I have an open loop pole, I can easily find the open loop control system transfer function. Now in similarly, if I want to find the closed loop control system transfer function, I need a closed loop pole. So many of you are doing is, now most of you are simplifying this transfer function. Now sir, this is forward path gain G of S by 1 plus G of S H of S. If you simplify this total, that is wrong, not required. Why? Because for finding time constant, we required pole's location. So the pole is available directly in the form of characteristic equation. Characteristic equation consisting of what? Characteristic equation consisting of closed loop poles. Therefore, you find the characteristic equation that itself will give directly closed loop pole. Now once if you get the closed loop pole, you can easily find the transfer function. Therefore, first we find the characteristic equation. This total is not required. What is the characteristic equation? The characteristic equation 1 plus forward path gain G of S into H of S is equal to 0. Therefore, 1 plus, what is the forward path gain? The overall forward path gain 10 into Ka by 1 plus 10 into S into H of S feedback path gain, which is equal to 1, which is equal to 0. Now this is the characteristic equation 1 plus 10 into S plus 10 into Ka, which is equal to 0. This is the characteristic equation. Therefore, what is the S? What is the closed loop pole? S equal to minus of 1 plus 10 into Ka by 10. This is the closed loop pole. This is the closed loop pole. Now minus of 1 plus 10 into Ka by 10. This is the closed loop pole, and this is the open loop pole. Now where is the closed loop pole? This is the closed loop pole. Now we can easily find the transfer function or not? Now this is the closed loop pole. Once if you find the closed loop pole, this is the closed loop pole. Locate the closed loop pole. Minus of 1 plus 10 into Ka by 10. This is closed loop pole. Once if you have a closed loop pole, once if the closed loop pole is available, now you can easily find the time constant of closed loop control system. Now what is the time constant of closed loop control system? The time constant of closed loop control system is negative of reciprocal of real part. This total is the real part. Therefore, minus of 1 plus 10 into Ka by 10. This is minus minus cancel, which is equal to 10 by 1 plus 10 into Ka. This is the time constant of closed loop control system. This is the time constant of open loop control system. And now what is the question? Now I am reading the question once again. The open loop transfer function of a DC motor is this. When it is converted into feedback as shown in the figure below, then determine the approximated value of Ka. Determine the approximated value of Ka. Find the approximated value of Ka such that the time constant of closed loop control system, one relation is also given, such that the time constant of closed loop control system is equal to 0.01 times of time constant of open loop control system. This is the question. Determine the approximated value of Ka such that the time constant of closed loop control system is equal to 0.01 times of time constant of open loop control system. That's what I'm giving, the finding the time constant of open loop control system, and I'm finding the time constant of closed loop control system. And in this question, options are also available. We just approximated value of Ka equal to 1, option A, option B, and this is option C, and this is option D. This is the approximated values of Ka, and this is the options. Therefore, now see here, the time constant of closed loop control system. What is the time constant of closed loop control system? 10 by 1 plus 10 into Ka, which is equal to 0.01 times of, what is the time constant of open loop control system? Time constant of open loop control system, which we are calculating, which is equal to 10. Therefore, now this 10 is cancelled. Therefore, 1 plus 10 into Ka, which is equal to, this is 1 by 0.01. If you go to that, then this is 1 by 0.01. 1 by 0.01 is nothing but 1 plus 10 into Ka, which is equal to 100. Now 10 into Ka, which is equal to 100 minus 1, which is 99. Therefore, Ka, which is equal to 99 by 10, which is equal to 9.9. 99 by 10, which is nothing but 9.9. Therefore, the approximated value of Ka, which is equal to 10. The approximated value of Ka, which is equal to 10. Now, this is option B is correct. This is a question number 6 in our handbook. Now, this question is asked in the previous year's GATE examination 2 marks question, which is very simple. See here, this question is, which is very simple, just based on the time constant concept, but he is giving for how many marks? 2 marks. That's what I'm saying. Once if you are perfect at the basic level, once if you are in the basics are strong, then automatically the questions which we can easily solve. Now take this one. This is question number 6 in our handbook. This is for 2 marks in the previous GATE examination. Okay, then we have a different types of inputs, which is nothing but a step input, a ramp input, or a parabolic input, right? Impulse input, and these are the different types of inputs which we are covered. And these are the inputs when we give these inputs. Then if you give the impulse input, then you can get the impulse response. If you give the step input, then you can get the step response. If you give the ramp input, then if you get the ramp response. If you give the parabolic input, then if you get the parabolic response. These are the different types of inputs and the different types of responses available, but you already familiar that what are the theoretical responses and what are the practical responses, which is useful response and which is not useful practically, okay? But anyway, we are doing the theoretical analysis also. Therefore, for doing the theoretical analysis, sometimes it is difficult for solving the question in the particular given response. So in such a situations arises, then we want to convert from one response to another response and one relation to another relation. Therefore, we want a behavior, we want to change, we want to convert the response from one response to another response or one input to another input. Okay. Now that particular conversions are which is very useful to you to solve that particular question within a shortest time. Therefore, for that particular solvation, for that particular easy analysis, then we want to doing for conversion of one response to another response and conversion of one input to another input. Okay, that we will see in the next session, and we'll solve a few problems based on that particular conversion topic also. Thank you.